All right, howdy. So, what I'd like to do is I'd like to talk a little bit about your lab. This is what I see your lab doing. It's going to take a person, which is you, and a motion detector, well, a position detector. I think this is a sonic position detector. That's how I'm going to talk about it. And you're going to produce some graphs of position versus time and find the velocity and things like that, the speed that you're going. So I'd like to talk a little bit about that in a little bit of detail, just to talk to you about what we mean by position and things like that, right? So in the real world, you'll be looking in a lab here. There'll be you and there'll be a table, and you're going to be some distance from it. Distance is more or less a concept from physics. It's the mathematization of the idea that some things are farther away and some things are closer to different objects, right? So it's sort of a mathematization of the separation between objects. So you're going to be some distance from a table, let's say, or from the sensor. I'm going to use the table here. And what we want to do to get an idea about what that distance is in physics is we sort of mathematize that. So what we're going to do is we're going to add an axis here. We're going to sort of add some sort of way where we can measure things. And we're going to measure, you'll probably be measuring in meters. I'm going to measure in feet. So we go over right at the table is 0. And then we have 1 foot, 2 foot, 3 foot, 4 foot, 5 foot, and so forth. So this is a distance in feet from the table. All right, so that's what you're going to measure. If you see right now you are at t equals 0, when you're starting this, you're 6 feet away. And now you're going to walk towards the table. So if you walk towards the table, first you'll, after maybe say 5 seconds, be 4 feet away if you walk slowly. And then after 10 seconds, maybe 2 feet away. So you'll go towards the table, and your separation is changing, which means the measurement of your distance is changing. And that's basically, each one of these is stacking one 12-inch ruler pointing away from the table. So if they're 1-inch rulers, you'll see that. Probably the tiles are pretty close to 1 foot. Usually they're about 1 foot, 18 inches by 18 inches, 12 inches by 12 inches, or 24 inches by 24 inches. You can sort of count those up once you figure out the size of one of them, and you'll be able to find out these distances. Now, if you stay in one spot, obviously, you're staying there, you haven't moved, and then you can walk back, and maybe you walk even slower back, so you go from 2 feet to 3 feet and 3 feet to 4 feet. All right? So that's just measuring the position at all of these places. Now, the point of this is sort of to find the speed that you're moving, the velocity that you're moving at different points along the timeline. So what we're going to do for that is we're going to need the separation, right? So the speed you're going between places is, the velocity is going to be the change in your coordinate position x, which is this distance d, over the change in the time, right? So in this case, that d is going to be the final, right? This is x final minus x initial over t final minus t initial. So your final position here is 4 feet, and your initial position is 6 feet. And if you divide that by the difference in those times, that's 5 seconds minus 0 seconds, or let's see, that's 2 feet over 5 seconds, which is 0.4 feet per second. Okay? So that's how you get the velocities. You just divide these two things from each other. You're taking this displacement and dividing it by the time, not the position. Time between those two things. Now we could do the same thing, right? You have another minus 2 feet. And then if you just stay in one place, you have 0 feet, right? It doesn't actually matter how long you're standing there in place. It's still 0 feet, and you're not moving at all. So right there, v is equal to, right, this is 2 feet minus 2 feet over 20 seconds minus 10 seconds. 2 feet minus 2 feet is 0 feet over 20 seconds minus 10 seconds is 10 seconds, and well, that's just 0 feet per second. You're not moving at all. And we can find the rest of those distances. So the displacement is just the difference between these two places as you're going towards the table. You've got a minus 2 feet for every 5 seconds. When you're standing, you have 0 feet for 10 seconds. And then for every 5 seconds, you have 1 foot going away. So what you're going to end up with is a graph. And with a graph, you do something like plot each one of these positions. So if we start here, right, our position is at 6 feet. And then here we have 4 feet. That's 5 seconds. So this is 15 seconds. This one here is 10 seconds. This one here is 5 seconds. So that's 4 seconds there. And then at 10 seconds is at 2. Right? And then if we come over here, it's 5. Okay, so this one's 20 seconds. So there's no dot at 15 seconds. We're just standing there for all of this time. And then for every 5 seconds, we go up 1 as we go away, right? So this is our plot, right? Something like that. So I'll plot it again. 5 seconds is 4, 10 seconds is 2, 20 seconds is still 2, 25 seconds is 3, and yep, ooh, it's a new one. 30 seconds is 4, and that gives us this line. And the slope of this line is the velocity. This is the same equation that we were talking about previously. It's delta x, right? This is delta x, and this is delta t. So it's rise over run, so the slope of this line ends up being your velocity, right? So this is delta t, and this is delta x. So again, we didn't do this one previously, so that's v is equal to, let's try these two, 3 feet minus 2 feet over 25 seconds minus 20 seconds. So that's 1 foot over 5 seconds, which is 0.2 feet per second. So that's the speed going there. So that's actually the velocity because it's got a sign associated with it. If it's minus 0.4, it's the velocity. And so we've calculated all those already, and that's basically what you're doing. But you're going to do this a little bit in a little more complicated way, because you're going to have something taking the data for you. You're going to have a Sonic Ranger or something like this. And this is interesting because the way this works is, at least to some level, I mean, not everything, but to some level, it's the same principle that you're measuring, right? That you're learning here by walking. The way this Sonic Ranger works is the same way that, you know, walking at a more or less constant speed would give you. So if you have a more or less constant speed, let's say these represent the sound waves, right? And they're moving at approximately 343 meters per second. That would be somewhere around, let's say 1,100 feet per second. So that, I mean, that's pretty quick. I'm going to guess that's around 750 miles per hour. But if you wanted to use it for something, look it up. So that's the speed of sound in air. So what do we want to do with this? Well, we want to watch this thing move. Everything, since sound is moving in the air, it's a wave, right? Just like a water wave is a wave. And the speed of the wave is determined by the medium, right? So the speed of the wave in air is going to be pretty much the same for everything, so that's why there's a speed of sound. The air is being disturbed, and it's the relationship between the air molecules that produces the speed of the sound wave. So the sound basically moves at the same speed no matter what the frequency is, no matter what the disturbance is. So this Sonic Ranger is, well, it's basically an active sonar, right? So this is the same principle. This makes a sound. You may or may not be able to hear it, right? If it's too high for you to hear, that's perfectly fine. It will still do the job. And that creates a disturbance in the air, and that disturbance moves. It moves at that 750 miles an hour, which is a little bit larger than the speed you're going to be moving at. So basically, it's instantaneous as far as your motion is concerned. You're so close to that Sonic Ranger. And when it hits something, in this case, it's going to hit you or basically a flat book so that it reverses and repels. The sound waves reverse and go the other way, right? Because the first one hits you and bounces off, the second one hits you and bounces off, and the third one hits you and bounces off. There's not a perfect reflection, but there's more than enough for the Sonic Ranger to pick it up when this hits. And then it keeps on going at the same speed back to the Sonic Ranger. And when the waves hit the Sonic Ranger, then it detects it. It knows when it sent out the wave and how long it took for the wave to return. Therefore, it can calculate a distance from that, right? The distance is twice this distance, right? The distance of the sound wave is twice the distance from you to the Sonic Ranger, right? Because, it has to go there and back again, 2x. C is that speed of sound, 750 miles per hour, let's say. And delta t is the time between when it sent the pulse and when it detected the pulse. All right. So that's exactly how sonar works. Sonar is a little more complicated for lots of reasons, but that is the basic operating principle around sonar. That's basically what you're going to use in your lab class, right? So, and that's more or less what you're doing in lab this week. So I hope that's helpful in whatever you need to do to get ready for lab. But I just wanted to give you a few heads up about some of the things, some of the concepts in the lab. All right. Thanks for listening. Bye now.